Welcome, welcome, welcome to this virtual town hall that's focused on CFD and how you can leverage it to accelerate your business. So I'm Joe Galliera. I'm going to be the host and MC for this town hall. And to get things started off, I just want to go through the short agenda with you that we have today. So after this welcome and introduction to our guest panel, we're going to go through a series of presentations that they have prepared to show it, and so that we can learn a little bit more about what they're doing and how they're using CFD in their business. And then we're going to open it up throughout the presentations and through the town hall. We're going to ask you to ask questions of us, of the panel, and then we can answer those during the virtual town hall Q&A. And then at the end, we'll have a closing and some documents and things that you can take a look at. All right. So this is me, Joe Galliera. I'm in Philadelphia, PA, but I cannot do this presentation by myself. Today we have two others of my colleagues. Andrew Gross is a producer. He's coming from Los Angeles, California area. And the support on the questions is Reza Tabatabai out of San Jose as well. And I'm broadcasting today from Philadelphia. Our guest panelists are these three distinguished gentlemen: Chris Watson, who is coming from Huntsville, Alabama; Dr. Joe Lacey from Madison, Wisconsin; and Jay White from the Portland, Oregon area. So welcome and thank you all for being a part of this great webcast. And we're going to get to know them a little bit better when they do their presentations. All right. So just a little bit of housekeeping first. Since you now know a little bit about us, I just wanted to talk and introduce you about who is out there, get to know you a little bit better. So we have people that are joining us from across the world. This is showing a map of North America. And we have several hundred people that are in this presentation right now. And we have this heat map is showing the locations in red where the majority of, there's a larger density of people. And you can see the Boston, Massachusetts area, New York, the Eastern Seaboard there, also on the West Coast, as well as several in the Midwest there from Minneapolis, Madison joining Dr. Joe Lacey, others down in Alabama, Texas, and what have you. So it's a wide audience, as I mentioned, and we're looking for a great discussion in the Q&A session that we have here. All right. So how are you going to do that? Well, let's go through, and I'm going to play this short little video that'll explain it to you. Now, everybody is muted, so the only way to interact with us is by the question section. And I also want to make a note that all questions will be logged. So if we don't answer your question live on screen, then we will have that recorded and listed, and we can address those to you one-on-one afterwards. Oh, let me play this video here. So if you click on the orange arrow button, as you can see there, that brings out the GoToWebinar interface, and then in the question section, you can type that in. So I'm going to play that one more time so that you can clearly see that in the white section there, and then you can hit the send button to send us, and that's, again, how you're able to interact with us. All right, so now that we're done with the opening, let's get right into the meat of it with our presentations. And I'm first going to introduce Chris Watson. And Chris is a technical manager with Mentor Graphics in its general purpose CFD group and has over 20 years of experience in CFD. His engineering roles through the years have included consulting, technical support, customer training, and pre and post sales application engineering. So now I'm going to turn the floor over to Chris and have him present.
Great, thank you, Joe. I will pick it up from here and put us into presentation. Yeah, thank you for the introduction. Excited to be part of this town hall with you guys. And really, I'm going to be relatively brief. I just want to sort of kind of set the stage with respect to CFD and the CFD landscape out there, and just sort of maybe give a little perspective as to how it fits into to product development at companies. And I guess the first thing to say would be that that CFD has just continued to grow in importance and usage in product development. I've been in the industry for since the 90s, and certainly back then I would have to explain what CFD was. If I was speaking to somebody, most people hadn't heard of it. If you weren't working at an aerospace firm or at an automotive company, big companies that could afford this type of technology to be part of their design process. But today it is much more pervasive, and there are several reasons for it. Certainly we get a big assist from the hardware side of things, where with each passing year you get more and more powerful computers, which costs less and less. The laptop that I have right here that I run CFD problems on is so much more powerful than this huge box that I used to run just 10 years ago. So with that, combined with, of course, increasingly easier to use software, better software, developments in commercial CFD over the past decades has also expanded the usage of CFD to more people. So it is a much more common technology in a lot more companies now. The other thing about it is, over time, the acceptance within these organizations and within management of these virtual simulation results is much wider. There may have been a lot more skepticism going back in time, partly from the modeling techniques that you had to do, limited, based on the limitations of your hardware, of the software you were using. You can run a lot more accurate types of analyses now, and I think these type of results, not just CFD, just CAE in general, are a lot more accepted and a bigger part of doing product development in general. And really, with that, you can put this into really all phases of the design process. It's always been sort of something at the end of doing product development, the verification step. With the different types of software available, it's a lot easier to sort of introduce this type of technology earlier in the design process, and incorporate CFD more easily. So with that, you also see this technology being used in other industries besides the big original ones: aerospace, auto, electronics, of course, has a lot of CFD and virtual testing in it. But things like consumer goods, for instance, 20 years ago, you wouldn't have seen nearly as many consumer goods oriented companies doing CFD. Medical, energy, process, and so many more, including the difference in size of these companies. Instead of needing to be at a big aerospace company, you can be at a small, lean company, and there are tools out there that can help you do CFD effectively. So really, in terms of how the software has evolved, I would say there are kind of two classic threads to it. There would be one, the way CFD has always been done, and that's to have a sort of standalone interface, a powerful interface, and everything in it is written for a CFD analyst to do that type of problem. And certainly this is the common direction that a lot of companies continue to pursue and develop. I've listed out just a couple of probably the biggest players and most well-known names in the space that have sort of this approach to CFD as a powerful technology. The other way that CFD has evolved is to much more tightly connected to CAD and embedded into the CAD interface and have it be a part of the CAD tool, essentially, where you do analysis directly in your CAD software, working on the native model itself. So that's another direction that CFD has evolved, sort of a second strain, if you will, and this approach has opened it up a bit more to, let's say, a broader group of engineers as well. So I think some of the presentations you'll see after this include, using that approach to CFD. So I've listed again a couple other of the players in that space. So so that sort of introduces you to CFD landscape in general. And from here, I'm going to hand it back over to Joe to go ahead and hand it off to our next speaker.
All right. So thank you, Chris. And maybe I didn't properly introduce myself either. I have about the same amount of experience as Chris has in the CFD industry, and I've also seen it evolve over that time as well. So that was a great overview to get us started. But what we're going to do now is, so your contribution to this virtual town hall is very important. So again, I'm going to remind you to ask questions, and you can easily do that in typing it into the section that is provided under the questions section, as you can see here. All right, so our next presenter, I'm going to turn off my webcam, is Dr. Joe Lacey. Dr. Joe Lacey is a senior principal mechanical engineer at GE Healthcare, and with over 40 patents, his expertise is in the following areas of electronics cooling and packaging design, precision temperature control design, system design optimization, and precision tolerance mechanical designs. You can contact him at Lacey Engineering. That's at Lacey Engineering at yahoo.com. That's LACEY engineering at yahoo.com. So go ahead, Joe, take it over.
So thank you for allowing me to talk today. I really appreciate it. This is stuff that I enjoy doing. So I'm going to give you a little bit of a flavor for what we do in GE Healthcare. Stuff that I'm going to show is just stuff I've done in the last, 6 months to a year at my new position in the anesthesia and respiratory care group. Prior to that, I worked on the CT CAT scanners, which was application that required hyper-precise temperature control on the order of like 0.5 degrees Celsius. Temperature change was the maximum allowable under any boundary condition shift. Unfortunately, it turns out that CT machines rotate at extremely high velocities, go from rest to 70 miles an hour in about 15 seconds. So challenging boundary condition shift. So a couple examples I'll go through today, and to put my experience in perspective, I'm a design engineer. So for me, CFD is a tool for creating and getting designs done quickly and accurately before we start prototyping. And I'll show you an example where we didn't do that, and that'll be in the ultrasound flow agent concentration sensor analysis. This was something that was ongoing before I joined the group. Simple electronics cooling example. Show you something new that we're working on, a agent injector, anesthetic agent injector valve, and some flow animations around that. So this was a project I walked into when I started in the group about 2 years ago. Over here, these are basic ultrasound flow sensors that were being developed internally to the group. They're kind of dual function. Purpose was not just to get flow, but also to get agent concentration. So when you have a patient under anesthetic, you need to give them a certain percentage of anesthetic gas, and you're feeding a medical gas at the same time, and you have no a priori knowledge of the gas that you're being fed. So it could be oxygen, nitrous oxide, in many different combinations. So that added a couple degrees of difficulty. So to get started, I was handed this kind of geometry. They were having problems experimentally and wanted me to see if I could work backwards using CFD to try to sort out what was going on. So I started with a steady state analysis, looking at flow velocities and profiles, looking at uniformity, impacts of geometry on flow straightening design. After that, I looked at transient analysis because it's a send-receive system, so flow pulsations can change the answers in between pieces of ultrasonic information arriving. Then move from there to look at how do we make the design work better. So on the right here were two original design concepts where there'd been a lot of empirical development. And then this was the proposed CFD-driven design that came out of my work. So here I'm just showing basic things that you can do with the tool. This particular case, we have a 100-to-1 turn down ratio on flows, so 0.15 liters per minute to 15 liters per minute. And in this particular case, there was a desire for packaging reasons to enter at 90 degrees and come out at 90 degrees, which is not a terribly good idea for getting good flow balance. And the attempt was to use some screens to try to straighten the flow out. And the assumption was that screens were also adequate for flow pulse dampening, which they are not. So here in a low flow case, just looking at some cross-sectional plots, how the velocity profile develops. What I'm not going to show, but I took and gridded this up and worked out. You can think of like flow tubes, looking at the average velocities, and then work that backwards into ultrasound calculations, because the ultrasound information you get a number for the flow. So you're getting an averaging of the flow field. And I looked at the impact of how these velocity profiles developed on the length, and that influences what you see. But here, you get a high core flow, it's fairly balanced, developing flow profile, low flows. You go to high flows, and you can see you get a very unsteady, unbalanced flow where you got a higher flow coming off up here, flow rates down here, you get very skewed profiles. This did not yield good results. Not a huge surprise. Then the obvious next step was put it in line. And one of the things, let me back up one slide here. Again, the presumption was in doing it in line, okay, you took care of these corner problems, but there still was a misunderstanding on what do you do about flow pulsations. So one of the things that I demonstrated using transient flow analysis. So the top view is what the flow is doing in time on a cut section plane. And you can see you got eddies forming and shifting, and the flow streamlines shifting in space. So basically the velocity profiles are shifting. So depending on when you get your information, you shoot an ultrasound wave from this probe, it's picked up by this probe, then you shoot back. That difference in time frame will give you differing answers. This is just a different view, using vector plots. And you can see there's definite flow imbalance. So these were things that I brought to this group to try to demonstrate what the tools can do, and that things that they were seeing experimentally could be explained through the CFD tool, which leads to the next logical step. How do you make it better? So that led to this design. Unfortunately, I misplaced the movies and didn't have time to rerun. So you just have these static shots. But by and large, by putting the transducers in line with themselves and flowing around in an annulus that has passageway depth to take out flow pulsations, I was able to straighten out the flow fields that the ultrasound transducers see, and you'll have to just take my word for it. When you look at the transients, you don't see the flow pulsations in here. They're being damped out by the narrow passageway. So it's just a game of tubing passage length, passage diameter versus allowable pressure drop to get the damping effect, but very old school approach to doing this. But it shows the power of the tool going from empirical attempts and lots of experimentation to being able to sort out what was going on and then turn that into a much more deterministic design. So when you get on the lab test bench, your odds of success are much higher. Another example, this is very, straightforward, very typical electronics cooling analysis that I had to do. This was an existing product, and what had changed was there is a new CPU board under this heat sink. The heat sink didn't exist, but the desire was not to change anything in the covers, to change any kind of layouts in the grill. So for instance, there used to be a fan over here pulling air out. For a variety of reasons, they didn't want to even change that. So it was, can you come up with a solution that'll make the new CPU board work, stay below 80C, work at 4,000 meters and an ambient 35C without changing anything other than adding a heat sink. So using, very standard techniques, 2 resistor models, thermal joints, PWB calculator to work out the board thermal conductivities, select a fan, create a custom fan curve, 2 resistor JEDEC model for RAM, thermal joints used to deal with the heatsink in RAM gap pads. And then the other nice thing is simulating altitude is very straightforward. This is an example of something that Chris had mentioned in his presentation. Because this geometry wasn't morphable and because it's a very convoluted flow path, this analysis didn't lend itself to making a simplified model. I really had to deal with the geometry as it exists. And that coupling of the CAD system to the CFD tool made this very reasonable, very straightforward. I mean, there's a lot of cleanup that you have to do. You eliminate, strip a lot of components off the boards, but that's pretty standard stuff. If you had to fake this out, as I had to do, say, 10 years ago, this was a pain in the neck. Now this is a week's worth of work, pretty straightforward. The tools have evolved to the point where they are unbelievably user-friendly and capable.
All right, thank you, Dr. Joe. I'm gonna just, I know you had a few other examples that you wanted to share, but we're running a little bit behind in time. So I just wanted to, that was a great example of showing you how you can utilize, how CFD can inform you in the design process and how you can utilize native geometry in helping you to, work with those convoluted flow paths and things like that. Now, so you have your PhD in engineering, but you didn't focus on that work at that time. You came into CFD later. Can you briefly kind of tell us how you got started into CFD and how you were able to get up to speed, and if there was any support that you had when you
Sure. So in grad school, my PhD work was on journal bearings, but wasn't applying CFD. But I took, the available classes at the time. Roll forward, start at General Electric in 2000, where they had some pretty intense electronics cooling problems, but they weren't cooling problems, they were temperature control problems. And because of the timelines, the kind of budgets involved in these projects, these are, $200, $300, $400 million projects, you needed to be deterministic. So we started using the CFD tools to do precision temperature control and get good predictability. And I can say this with a straight face, literally we spent 9 months worth of modeling, built the design, tested in the lab, it worked, went into production. We never had to adjust anything other than the controller. So that was the power of it, but it was mainly to drive design as opposed to doing analysis. It was clean sheet of paper design. It didn't exist. Use the tools to develop the design and guide the architecture.
Okay, Well, and the second part of that was you. Was there any support that you used to get up to speed on it?
Well, so when we started doing the Safari, the CAD and the CFD wasn't that well integrated. So in those days, it was a lot of ad hoc back and forth with the company that did the CAD, did the CFD tool. We used different CFD tools. We had to mix and match. You roll that clock forward to today, the stuff that's in my presentation, this is all integrated into, I'm using SolidWorks. It's all Flow EFD integrated in. Here, now I can get great support. So when I pick up the phone or I have a question, I get pretty much instantaneous support. Very different than when I started doing this stuff in 2000. You spend a lot of time figuring things out on your own.
Right. Well, that's great to know, and that's really important when you're dealing with any software product. So thank you, Joe, for a great presentation. And what we're going to do now is, again, if you have any questions for Dr. Joe about his presentation, please type those into the sections that we have provided. And what we're going to do now is switch it over to Jay White. So let's make him the presenter here. Jay, you there?
Yeah, hey, hi.
Let's get you, there we go. Excellent. So Jay White, he's the CTO of Falcon Pursuit and has been a top flight R&D leader for Fila, Adidas, and TaylorMade Golf. He's a design engineer and technologist for high performance vision systems and 3D surface scanning. He's an aerodynamic specialist for human movement and products designed for athletes, having spent many years performing testing in a wind tunnel. He's also quite an accomplished athlete himself. He has 12 US patents in body scanning and applied aerodynamics, with more than 38 foreign patents in footwear and human body metrics. So Jay, the floor is yours.
Sounds impressive. I'll jump right into it. Nothing we do at South Falcon's Pursuit is considered normal. Both Joe and Andrew have been out and spent a little time with us, and we're definitely a strange company. So typically we answer questions that everybody knows the answer to. How smooth should my Ford F-150 be, and do I want to hyper polish my Tesla Model S? And as it turns out, you probably don't. So we use a hyper-realistic modeling format, and our basic premise is simulate everything and have everything in the simulation. So when we're working with autos, wheels rotate, tires have treads. You can look inside the Tesla and there's a don't panic screen up on it. Why would we model the interior of a car if we're testing for optimized aerodynamic coatings on the outside? Well, if you turn on the vents, you have a different modeling constraint on how the flow goes through. So the entire basis of what we do is the very best, highest precision models we can utilize, because at the end of the day, we're dealing with somebody who knows the answer. You drive your car, I know the answer. You wear a helmet playing football, I know the answer. If you're a cyclist for the Tour de France, you put on a go fast wheels and helmets, I know the answer. And typically the answer you're applying is not the correct one. So in the case of the Ford 150, which is a brick in the air, we're able to give it 0.5 mile per gallon just by painting it better. And for your Tesla, about 5 miles per charge. UAV, things that fly through the air. Hey, the slicker they are, the better they go. And Falcon Pursuit has specialty. One specialty is we're typically external. And the other specialty is we work from 1 mile an hour to 134 miles per hour, typically cycling, Formula One, slow flying aircraft, fast driving cars. And because of that, we have a very good feeling for what is a reasonable answer. So if I have a runner who's running in a marathon and he's got flippy floppy clothing on, what should the drag be? And since we have two highly experienced aerodynamic dudes, James Homestool, who is our CEO, and myself, spent 3+ years in one of the better low-speed wind tunnels. We have a very good idea of what the answer should be. However, what we will cover is you got to make sure your simulation is correct. A wind tunnel, athlete strapped to a bunch of balance beams, held vertical, wind rushes over them. That's not the real world. In the real world, an athlete's moving all over the place, and he runs through still air as opposed to air being blown over him. So for a Scan Eagle, we can extend the range 51 kilometers per tank, and a Puma, which is an electric-driven forward prop, we can give it about 4 minutes of airtime. In our simulations, propellers rotate, wheels go, athletes' legs churn. So having static stuff is great, but it doesn't mimic what we're doing in the real world. Classic, you have a downhill skier, upper left-hand corner, Alexander Kilde from the Norwegian team. Lower left-hand corner, Lindsey Vonn. Courtesy of Red Bull, we were given access to a Lindsey, scanned her in 3D, put her in a downhill position. Courtesy of our friends at Oakley, we tried some different textures in different areas. So this is a classic real-world situation. A real athlete in a real position. Well, what position do you put an athlete in? You just go, hey, there's a downhill tuck. We have a very special capability where we can take video and then overlay your avatar onto the video and make sure that the position we're testing in aerodynamics is actually a Lindsey Vonn tuck position. So notice her hands, her feet separation, the tilt of her head. All of that is hypercritical if I'm going to give her a correct answer. So as it says, the Olympic course length, 2.87 kilometers. Time on the course in the specified body position, turns out to be 67% of the downhill. Lindsey's in or near that position. Headspace drag, well, that's the drag of the helmet, goggles, strap, chin. And when you add that all together, if you do it correctly and you texture it correctly, you can give an athlete a true 1.5 second course advantage just by painting their helmet a little bit better and putting the finish on their goggle strap in a superior area. Tour de France, everybody's seen Tour de France. You got cyclists going ultra fast in a time trial on the left, and you've got him riding up on his drops on the right. Cycling is pretty classic. If I reduce the grams of drag by 100 grams, they're going to go 1 second per kilometer faster. I don't care if you're Joe Average riding 13 miles an hour or whether you're a top cyclist going 38 miles per hour. So as long as the power stays the same, if we reduce your drag, you're going to get there sooner. The key to this stuff is when you're dealing with an athlete, you can see the athlete in the upper left-hand side, it's got a disc wheel in back. Disc wheels are pretty interesting. If you're in a wind tunnel, they're going to be fast. If you're in the real world, there's virtually no scenario on the planet where a disc wheel is going to allow you to have less drag than two well-designed aero wheels like the front wheel on it. So, and that's just a classic. You go to a race, all the big guns are wearing disc wheels. Guess why? Because the guy who ran and won last time had a disc wheel. So that's the typical mentality is when we're dealing with athletes, if you just throw signs at them, they go, huh, I'm going to do what the winner did. Because when I was an athlete, that's what I did. So we have to have a method of presentation that actually gets the athlete involved. Like, hey, wear this helmet a couple times and see what you think. And real world relationship to it. So if we take an athlete and we put him on a track and we have him buzz around with the helmet and we monitor his power, we can give a pretty good idea of whether we've helped him aerodynamically or whether we've hurt him. It's not as precise at CFD, but it's important. Then if you look at the top right and the bottom left-hand picture, the athlete gets there before they get there. So they disturb the air several meters in front of them. So it doesn't do any good to stick a helmet out there and test it all alone, because you can make the helmet itself brilliantly fast, but when it gets put on the athlete, it actually slows them down. The next generation stuff we're doing is we're working with surfing athletes. And in those surfing athletes, we've got the wave, we've got the board, we've got the athlete, we've got the air. And those are now multi-physics. You got to do hydrodynamics on something that's not a flat piece of water, and you got to get the surfboard to cut through it in a reasonable manner. And you got to make sure that under a big wave forms its own wall of air in front of it. It gets to be a really complex. So without CFD, you're pretty much lost. So how do we do it? We need to create a virtual human. We need to do that rapidly. When I first started doing virtual humans, it took me a week to put one together. And now we have automatic engines. So that's Ian Walsh, the surfer you saw in the previous one. We put him on that platform. He hits a button. 31 seconds later, the data collection's done. And then 2 minutes later, I've got that guy in the middle, which is Andrew, fully rigged, stripped of everything but his underpants, and he's ready to be put in an athletic position. So Falcon Pursuit has a technology called ARE, Autonomous Rendering Engines, that allow you to put humans in any form in a couple minutes, where when you do this all on your own, it would have taken a couple days. The second thing is, once you have the athlete, how do you position them? So what we use is a 2D to 3D technology that takes video snippets, and then we can dump the avatar onto the video snippet and make sure it's in the correct position. So we're taking 2D, turning it to 3D, because to put motion capture on an athlete that's on a wave that's 300 meters from you, and he's traveling at 20 meters per second, I mean, it's hard to get just good video on him. So we have to have techniques where we can position the athlete in a day of the competition position. Otherwise, the analysis you're doing for him is completely theoretical. And this is why CFD has a huge advantage over wind tunnel, because if any of you have been in a wind tunnel strapped down, you take a very unusual position. Yeah, it's you, but you know you're being analyzed. When you're out racing, you take your position. So I got to have the body position set by a race position, not by some funky stance you have in a wind tunnel. Then you got to have hyper accurate solid models. Usually the banter in CFD is simple, 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 and we do exactly the opposite. The reason is, if you show that ski boot to a fifth grader, he's going to say, yeah, that's the ski boot that Alexander Kildee wears. If you put just a box down there and say, hey, it's easier for CFD, the fifth grader doesn't believe you, and Alexander doesn't believe you. So when we're dealing with specialized bikes, Oakley glasses, Christensen surfboards, Giro helmets, or head ski boots, it's got to be the real thing. It can't be like kind of, because when you run air over it, if it doesn't have its real shape, you haven't got a real world solution. If you're going to be accurate, you need to know your boundary conditions. So like I said, wheels rotate, but even more important for that, you just don't blow air over an athlete in CFD. You move the athlete through very calm air. The reason is when you blow air over a surface like a road, the first 6 to 12 inches of that road are going to have substantially less velocity than just above it. So the air attaches to the road and rumbles. And if you've ever been in a wind tunnel like we have, we notice this all the time. And that ain't real world. When my bicycle rolls with me on top of it over a road, there's the boundary layer of the air sitting on the road is like maybe a centimeter. It's not 40 centimeters. So knowing boundary conditions allows you to monitor your CFD and make sure you get a real world result. Got to know the math. When you're dealing with airplanes, it's just don't make it more slippery. You have to know the lift to drag ratios, and you have to know how that applies to range. When you're dealing with an electric car, you just don't go make it smoother. You have to know how its coefficient of friction, funnel area, affect the range, and you got to plug those into equations. So when I say you get 5 more miles on your charge, it really is 5 more miles. So we work with the US Ski Team, Red Bull, Oakley, aircraft companies, and the main thing is CFD allows us to communicate. So I can show that picture to a fifth grader and I say, everywhere that's red, that athlete has high pressure. Everywhere that there's blue behind him trailing, it's a low pressure zone and he's getting pushed into that. Then I'm done. So now my fifth grader can interpret my CFD and goes, oh, Jay, I see where he's getting pushed and I see where I might want to put some design intelligence so that we can make a better product, make the athlete go faster. So typically, we don't work typical. We're a crazy company at Falcon Pursuit. So Oakley will come in and they'll literally have me for 60 days, 24/7. That means at 2 o'clock in the morning on a Sunday, if one of their designers wakes up and goes, hey, I want to try that, they'll pop it to me and I'll have run a CFD from 2 o'clock in the morning until 10 o'clock the next day and going, okay, here's what we have. So we're dealing with designers and athletes, and both these have limited attention spans and they got a job to do. Go ride your race, design a new helmet. So when we get a design iteration in from them, typically within hours, we have to have a result. And that's one of the strong points of the style of CFD we have through Solidworks is I don't have load in times, load out times. Once I get my design done, I'm meshing and calculating immediately, which saves me a huge amount of time. Results are provided next day, early afternoon. And just so you know, Falcon Pursuit is a churning engine. We did over 600 sports simulations of unique content, different body, different piece of equipment, or different velocity gradient in just the last year, plus all the other projects we work on. End of the day, don't be a drag.
Thank you very much, Jay. That was an excellent presentation. I think a lot of people that are in the audience, as well as myself, I'm still astounded at what you guys are doing there at Falcon Pursuit. Now, what you use this term hyper-realistic models, which is currently not the norm in CFD even today. I guess from me and from other people, they're just like you said, you have this churning engine. How do you do it? I guess.
Well, that is an awesome question. The creation of the models is the most stressful part of our business. So when we're dealing with companies, the first thing we have to train them in is how to deliver a great model to us. So the first models you get from a company are, they're not surfaced correctly. They don't have a true thickness. They don't have the material specified. They don't tell me how they're painted. They just go, here's our helmet. And after you work with them a while, then you tend to get very sophisticated models. The Ford F-150, great, awesome model. It actually came from Ford. I asked very politely, and they delivered me one. And it's accurate down to the individual bolt, which poses a very interesting problem. Has anybody ever figured out how many individual components can you have in a drawing in SolidWorks and not have the save engine conked out? And I actually know that answer to plus or minus 15 components. You can run simulation on virtually anything, but if I can't save it at the end, it kind of makes it frustrating if I just went through, painting all the doors and sticking them back on the vehicle. Right. Then a lot of it's just ingenious. I have a whole cadre of support personnel. So if I have a Giro helmet that's coming in and I want to check an actual helmet that's been delivered, there's very tried and true reverse engineering companies, but they just don't reverse engineer it. They have to create the correct thickness of the liner, the correct thickness of the lens, the correct orientation of the strap. So when I plunk that on the athlete, it's true, true, true. So Joe, you hit it right on the head. Models are the foundation of Falcon Pursuit. And that's also why a lot of companies come to Falcon Pursuit, is because we do humans better than anybody else, and we do them rapidly. And one of the most stressful things is putting a 1 millimeter thick suit perfectly over Lindsey Vonn when she's in her downhill position. That ain't easy. But if I don't do it, then I can't determine accurately what her drag is for that particular situation. So
now, Jay, I mean, you have those hyper-realistic models, but at the end of the day, when you go into the CFD, all you have is the mesh, right?
Correct. And what we do is that we tune the mesh so it delivers a real-world result. So if I got Lucas from United Healthcare and I've got him on the road and I've got him in the wind tunnel, I know that Lucas is 1,900 grams of drag for his entire bike, Lucas. And he's probably one of the best I've ever tested in the wind tunnel in terms of lowest drag. So if I set up a mesh on Lucas and he has 1,200 grams of drag, which is 33% difference, that is not a good mesh for me to use. So I actually tune my mesh to the real world results, and then I don't play the game of more mesh is better. And that's one of the true strengths of Falcon Pursuit in sports is our meshes are tuned to derive drags that are real world representative of that athlete at that altitude, at that velocity, with the cross currents and the air density all factored in. And we have a whole group of smart guys that do nothing but take these helmets out, plunk them on athletes, have them ski, a 1 kilometer stretch section at Copper Mountain way early in the morning so there's no air. And we can develop that meshing so that it gets me that level of result. So we're a little different than, we tune meshes not for better meshes, we tune meshes to make sure that when I talk to an athlete, the deltas we're representing are what he can actually achieve in a real world environment.
Excellent. Thank you, Jay. All right, just checking on a few things here. So we're going to go to our next presenter. Again, I'm sure many people might have some questions for all of our panelists, Dr. Joe, Jay, and Chris. So remind you how to do that. And I will go back to, let's get Chris here. He's going to just briefly talk about one of the biggest uses of CFD is in thermal management. So I'm going to ask him to just talk about that a little bit and how that is used.
Great, thank you, Joe. I will pick it up from here. And yeah, Joe asked me just to touch on thermal management briefly, just to sort of round out some of the examples that were already being presented from the other panelists. So certainly thermal management, in particular electronics, is a big area of CFD usage. These devices have thermal management issues, that affect their reliability, their lifespan. So being able to do good, effective, efficient modeling of these devices is really important. And of course, there's a desire to be able to do it virtually rather than always have to rely on physical testing. The range of these devices goes from really small down to the IC level on up to systems of systems. So there's quite a range of scale to what you ultimately need to model. CFD at this point has tools that can satisfy this entire range, and this is an area that CFD has been applied really for since the 90s. 90s is where it started to grow the use of CFD to do this thermal analysis of electronics. So just a couple or two or three trends out there that support the need to be able to do this type of testing. Of course, we know most people are familiar with Moore's law, relating to the number of transistors on a chip and doubling every 2 years. I've plotted up here a couple other kind of interesting data points, which includes things like the frequency and the power as you go over time. So although the transistors has continued along that law, it'll eventually have to flatten out at some point, but it hasn't yet. The things like the frequency on a chip or the power required, you see that in about the mid-2000s, it sort of plateaued. And really, if you think about it, as the frequency reached the point that the power density required to continue to improve the frequency got over about 100 watts per centimeter squared, the cooling requirements became so great that it just became increasingly expensive and impractical to continue to pursue that as a way of speeding up processing. So what ultimately happened is there was a shift towards using more cores. So it wasn't so much about trying to to increase the frequency of these chips, you got your speed up computationally from using more cores. And you see that those black dots on the bottom of the graph taking off at about the same time that the frequency and power plateaued. So to an extent, it isn't the only reason, but one influencer on the direction that computing took was just the thermal management issues. Another area that's very important with respect to thermal management, electronics, automotive, and transportation. If you go back 40 years ago, these were much simpler devices from an electronic standpoint. Today, these are rolling computers. There are computers and boards and chips all over the vehicle, and even the powertrain now a move towards having that be electrified as well. So there's electronics everywhere and electronic sort of thermal management that needs to be done, and of course the efficient way, if possible, once you have confidence in the accuracy, is to do it virtually. And then just one other area that is a trend these days is the whole Internet of Things. All of these, what used to be relatively mundane devices and appliances, all apparently need to talk to each other and connect to the internet. So all of a sudden, everybody has some onboard electronics, and that needs to be managed thermally. So certainly this area isn't going away. So there are a few different approaches to tackling it. One would be with the CAD integrated approach that we've already seen with our prior two panelists, Dr. Joe and Jay, including Dr. Joe showed some thermal management examples. That's certainly an approach. And when you do that, a lot of times there might be a module or two that you would add to your base package just to give you a bit more specific capabilities relative to electronics cooling. Certainly the general purpose codes still have a place, especially as you get into more complex physics, things that maybe go beyond the scope of what a CAD embedded tool could do. And you just need a bit more flexibility and capability. You can go to that style of tool. And then in this space, the other common and popular approach would be to take an application-specific CFD tool. So rather than CFD being so general, you saw, we've already seen a bunch of examples that are so diverse. Flow over Lindsey Vonn versus these small internal flow devices that Dr. Joe was showing. If you go ahead and know that what you're going to analyze is specific to these class of problems, these electronics cooling problems, you can really tailor your interface to that set of applications. And so there, that gave rise to software that was specific to just doing electronics cooling. So the inputs that you give it and the output that you get from it is more tailored to your needs. So that's kind of how CFD and these thermal management for electronics problems has evolved.
All right, thank you, Chris. And that was a great overview. And the first question is actually for you. So if you could come on camera and join me. So this is the live town hall question and answer session, which is what we've been waiting for. So now we know all of the panelists much better. We can find out a little bit more about the questions that are burning here that you want answered. For me, this is what I've been wanting to do, is to talk about CFD. And I have these conversations quite frequently with many people. So to share that with you and doing it live here is awesome. So let me get the first question queued up here. Just have to go. So Chris, what are the benefits of a traditional CFD tool, and how does it compare to a CAD integrated CFD?
Okay. I guess I'd put it in a few categories. One would be a little bit based on your expertise to begin with. You know, if you had a background in CFD, you know, having a specific tool just for doing CFD, knowing all of the options, all of the flexibility and bells and whistles of it, you know, might be appealing to you. There is also oftentimes with a standalone, a traditional CFD tool, there can be a potentially broader range of problems that you could tackle, some more exotic types of flow analyses. A CAD integrated CFD tool, and we could use Solidworks flow simulation or flow EFD, for example. They oftentimes tackle sort of the large, you know, meat and potatoes range of CFD problems, maybe 80%, 85% of the typical problems that you might encounter. And then the more sort of complex or exotic types of applications, those are probably better left to a sort of a classic CFD tool where there's different models that you have to choose in terms of, let's say you're doing like spray modeling for a fuel injector with atomization and vaporization, and there's like different models of that phenomenon that you need to choose from. A classic CFD tool interface would let you choose those different modeling approaches, but that comes with expertise. You need to know what to choose between to begin with. The thing you give up a lot of times though in that interface is ease, especially dealing with CAD. Invariably, if you're in a commercial or an industrial CFD situation, the geometry that you need to analyze is going to come from CAD. So that's going to need to come into your third-party tool. Hope you don't have any translation issues. Clean it up. The meshing is sometimes more arduous, whereas for the CAD integrated tools, and I'll speak specifically to flow simulation, it is able to take much more of the real CAD geometry, a lot like what Jay was showing, where you don't do any simplification. You can just give it the real model, let the mesher just chew it up, and be able to give you a solution. So the dealing with what is oftentimes the slowest part of doing CFD, which is dealing with the real CAD model and meshing it, a lot of times can be handled maybe more easily with that CAD integrated approach.
Yeah, I mean that is so true. In the days when I was working in the aerospace field and industry, I felt like I was spending all of my time doing the meshing part of it and not getting to the results. So that in many ways is still the case and what have you. So we're going to come back to this topic, I perhaps, but we're going to move on to Dr. Joe. The next question is for you. So if you could come on camera, and I'll start asking the question. So this is a leading into this discussion in a way. So the question that I see here is, can CFDs be used to tell you what the design should be? It seems like you're approaching from the perspective of what you have to work with. So I guess what they're asking is, can you modify the design or allow the flow or the software to show you how the design should be?
So the short answer is absolutely yes. Some of the examples I showed were just problems I happened to solve when I got to my new position here within GE. But for instance, that ultrasound probe, I did the initial modeling because that's what existed to show what was going on. But then I just started with a clean sheet of paper. And that is more typical of the work that I've seen done within GE Healthcare, where we use the CFD and or structural FEAs to drive the design. So you're starting with a clean sheet of paper. You obviously have to come with an architectural framework, design concept. But then you do parametric studies. We did a lot in my old group. We did a lot of numerical DOEs, use the DOE tools to curve fit the design space, hone in on where you want it to be, and then go back and remodel. You just don't blindly, run parametric models. You burn a lot of time and you won't actually get anywhere. So it's a combination of old school DOEs and the CFD or structural FEA. to drive the design.
Right. So I mean, in fact, actually, in a CAD embedded environment that you're working in, it's actually much easier to make changes to the design and see how that affects the flow, rather than having to do this process of going back and forth between the CAD to generate that geometry and then push it over to the CFD tool.
It's much easier when you have the CFD embedded in the CAD. But when I started my career, when I was in grad school, those options weren't even available. You can do it with traditional CFD codes. It depends on the complexity of the problem. Sometimes you are obligated to have the higher capabilities, but the way you approach it is the same. It just takes you more headache in dealing with geometry and meshing.
Yeah.
But your approach is identical. It's just there's an additional tax, if you will, that you have to handle.
I will mention just real briefly that this tools that I used now on a daily basis have been around for. Well, I've been using it for 15 years, and it's been predating me in using that tool. I just didn't know that was available. So it has a history of over 30 years of being CAD embedded. So I just want to make that point. Now, the next, there was another question for you, Joe, Dr. Joe. What tool would you use to simulate burner gasification following the chemical components throughout the process as it flows from the burner through ductwork into a dryer?
So again, it depends what you want to know. So for instance, if you're trying to model the combustion process itself, that's tricky. I won't call myself a CFD expert. There's certainly people within GE that do that type of work for us. But say for instance, CFX, Fluent, with a lot of hard work, you could model that. But then once you know the gas species downstream, those same tools could be used, but also tools like FlowAFD can handle gas mixing, as long as you're not looking for chemical reactions.
Mm-hmm.
So it's very different if you're, say modeling a catalytic converter with those continual chemical reactions. Then you need a more sophisticated code, but you also need to be an expert.
Well, right, and now it is very true that you have to be able to capture all the physics that is involved in a problem to make the proper decisions moving forward in the design process. But we do the same thing if we're doing upfront analyses. We might do a 2D analysis, which is really, we're simplifying it down. We're removing some of the physics, but that's informing us of certain aspects of the design. So you could say that there does exist a capability, if you have to do a combustion or something like that that is not handled by a particular tool that you're using, you could do certain things up front, simplifying it, maybe applying heat, power that's generating that heat, if this is something that you want to involve or look at. And then later on in the design process, at the end of it, you want to get a more absolute accurate answer. Then you could involve all the physics and hand that off to a specialized team that can do that.
Yeah, and a problem like that, typically the way I would look at it, I would split the downstream from the combustion process. So you could parametrically assume your gas species, the temperatures of the gas, do a parametric study, map the design space. What would the ductwork want to be downstream? Then you apply that as an input boundary condition to the combustion model, or vice versa.
Right. So thank you very much, Dr. Joe. Chris, the next question is for you. Looks like people were asking questions as we went in the presentation. So those of you who are waiting for Jay to answer some questions as well, we'll get him on the screen. But Chris, if you could come onto the camera again. So it's great to see. The question that we have for you, Chris, is it's great to see the extreme capabilities of CFD. However, I have a much simpler application. What can I expect as far as design time for an accurate model of fluid flow in a condition open to the atmosphere? I guess they're asking about maybe natural convection or something like that.
Sure.
Yeah.
Yeah, absolutely. You know, that it is sort of the focus of a tool like flow simulation, is being able to, especially if once you've, you know, gotten up and running and have run a case or two, and have gotten comfortable with the software, to be able to, you know, it could be, you know, that same day that you take a simple model and have turned it around and have already set it up and run it and are looking at results. You know, we have lots of customers where that is their experience. You know, it does, you know, a factor certainly is the complexity of the model. So there's, you know, there's some cases that would be a couple days. You could have something that's a longer running analysis just because you have a high cell count on your mesh. But yeah, there are plenty of experiences where it's, you know, within that same day you've turned the whole thing around. And just one side comment on the whole combustion discussion. With Flow EFD, which is sort of, let's say, the sister product of flow simulation, there are options with respect to doing combustion and actually then tracking the combustion products. So you do have a little more simulation capability, including modeling the combustion.
And so, Chris, you know, thank you for adding that. There was another question that came up here, and this is something that I often have to address myself. You know, maybe because of several factors, but this next question is, how accurate is the analysis made by Solidworks flow simulation compared with, say, another tool like ANSYS Fluent or CFX or the Siemens CD Adapco Star CCM Plus and what have you?
Sure. No, it's a fair question, and you know, there are lots of reasons that people might question potentially the accuracy. You know, they can see the ease of use, they can see the pretty pictures that are being generated, but partly because of even how it's marketed and the emphasis on being able to do CFD easier. You know, there's a tendency, you know, nothing in life is free. And you expect that there's probably some trade-off, and it's likely then to be accuracy, because that's what you're left with, because you can see, you know, in a demo setting, you know, including on your model, how much easier it potentially is than other approaches. This software is written by, it goes back decades. It grew out of the aerospace industry. We have a stringent set of validation examples that we run through. There are, you know, customer stories. Dr. Joe, I'm sure, could come back on and attest to its accuracy relative to his applications, but we have, you know, a host of customers who that is their experience as well. Really, the thing you got to think about is if it falls within the physics of what the software can model. And again, this gets back to my discussion about flow simulation can't do every type of CFD analysis. There is, you know, that top, you know, 10–15% of applications that aren't within its capabilities. So if you are within, though, something that is the software is capable of simulating, you can expect results that are on par in most cases with something like an ANSYS or a STAR. You know, if you follow good modeling practices. And actually, one of the things that does even help you buy back some accuracy is the accuracy of the geometry that you end up simulating. You don't take a lot of shortcuts with respect to simplifying the geometry. So geometrically, it's very accurate. The mesher, once you know how to use it, you know, with a couple simple inputs, can very accurately capture that. And the approaches that we use have been around and have been developed since the 90s, and it is an accurate CFD tool.
Hey, so Jay, I'm going to ask you to come on screen because we haven't heard from you yet. And the one thing that I'd like you to do is, I think you had a slide that you had investigated many different tools in your investigation of the technology for Falcon Pursuit. Could I make you the presenter and show that slide that you showed me before? Okay, so Jay, let's make you're unmuted now.
Oh yeah, just give me 1/2 second.
Sure, no problem.
Okay, tell me when don't be a drag is up, and then I'm ready to go.
I see don't be a drag.
All right, time. We all live in a must-have world. So seeing as we're such an extreme company, typically when I come off a high mountain and I'm deprived of oxygen and I want to do some comparisons. So what I did is I got a hold of some of my friends and I said, hey, we got a cyclist model. We need to start from ground zero, load them in, verify the surfaces, mesh to a particular configuration, generate the mesh, solve it, give you my answers. And when we did that on the same CPU, 48 core Intel HPC, birth to results in Fluent was 16.5 hours. Solidworks was already loaded in, so I didn't need to reload it. Geometry verification was 8 minutes. Setting up the project, another 5. Meshing 53, and the solver at the exact same number of fluid cells, 6.9 hours. So birth to death was 8 hours. Then we did something very hard to do, but I handed it to somebody who didn't know what the answer was at our friends from ANSYS and said, what's a total drag? And this particular model is not a single person, it's a real person. His name is Ward. He's been in my wind tunnel on numerous occasions on numerous bikes. Plus I have real world results from him. And what we found is that the ANSYS result was 20% off the real world expectation, too low in drag. And the SolidWorks results was about 2% low of his real world drag. And you can say real world drag, Jay, was that in the wind tunnel or was that, out on a time trial at the, a Velocidome where we monitor them very specifically? And I say it was both. So in our particular, taking longer to do a more accurate job, but accuracy for us is does the CFD have any reasonable replication of what we're going to see on the road? And if the answer comes back as no, to us, it's a much harder sell. Yeah, hey, we put you into a particular situation and it matches nothing you've ever seen before, as opposed to we put you into a particular CFD situation, and it comes back reasonably correlates. When we add drag here, it shows up. When we subtract drag there, it shows up. So, in a nutshell, these are real CFD problems that we apply to both systems, and it's both a time constraint and an accuracy constraint that we had questions about.
All right, well, thank you, Jay. That's, let me take back the presentation. So we're going to, I think we've covered a lot of territory here, and myself, I could go on talking for hours in this discussion, but I know you guys all have jobs to get back to, so we're going to conclude this. If you'd like to see more of stuff like this, please let us know. You can make the comments also in the question section, or when asked about that later on, you can do that. So let me just see here. So we have some, to close this presentation, we have some technical white papers that we'd like to share with you about specifically the Solidworks flow simulation CAD embedded CFD solutions. And in your interface, the way to do that is just open up your same GoToWebinar interface there and click on the handouts, open that up, and then click on each one of those handouts there. So I'll show you that again real quickly. So just clicking on those, you can download those for yourselves. And then I would just ask you, if you're interested in learning a little bit more about what flow simulation offers, please visit our website here, which is listed at solidworks.com/product/solidworks/flow simulation. Now, you don't need to know that entire URL. If you go to the Solidworks website, you can navigate to that through the simulation solutions. All right. So we're going to conclude that presentation for today. And as I mentioned before, all your questions are logged. So if you'd like to, we'll get back to you and answer those questions. So thank you very much for joining today's presentation, and good day to you all.